The goal for today's lesson is to be able to classify, graph, and compare real numbers and to find and estimate square roots. So we're going to go through this hopefully kind of quickly, and this prepares for a standard. This doesn't really cover a standard because this is something that you should have already covered at this time, but I want to refresh your memory before we move on because it's preparing you for the standard NRN B3, which is to explain why the sum or product of two rational numbers is rational and an irrational number is irrational. So, got to be able to know what rational and irrational are to be able to draw these conclusions. So we say that a number A is the square root of a number B if A squared is equal to B. So square root is the key word here that we're going to be looking at. And once again, I'm sure this is probably review, but for example, we say that 7 squared is equal to 49. 7 times 7 is 49. So 7 is the square root of 49. We're asking ourselves, what number do I have to multiply by itself to get 49? And whatever that number is, then that's the square root of 49. So we've got different parts to the radical. The radical is the whole thing, the way that it's written, this whole entire square root of 49 is called the radical. Now, the red part is known as the radical symbol, and then, of course, the number underneath is called the radicand. So 49 is the radicand. The radical symbol is the square root symbol, and all of it put together is called a radical. So I just listed the first 20 perfect squares for you. If you need to pause the video so that you can list these out, then you can, because we will be using these a lot. It's great to go ahead and start trying to memorize these. Maybe make yourself some flashcards. Know that the square root of 1 is 1. The square root of 4 is 2, because 2 times 2 is 4. The square root of 9 is 3. 3 times 3 is 9. When you keep on going all the way up to 100, we know that 10 times 10 is 100. We could go over here. Square root of 400 is 20, because 20 times 20 is 400. So in biology, lobster eyes are made of tiny square regions. And actually, I had the opportunity last year, Miss Basler across the hall, her class brought in some cicadas is actually what they brought in, and then they also brought in some lobsters, but I was looking at them under the telescope, and lobster eyes really do look like that. It's really cool. So just a little fun scientific fact for you, but lobster eyes are made of tiny square regions, and under a microscope, the surface of the eye looks like graph paper. A scientist measures the area of one of the squares to be 386 square microns. That's really, really, really small. What is the approximate side length of the square to the nearest micron? So basically what this problem is saying is we're going to estimate the square root of 386 by finding the two closest perfect squares, if we're going to estimate it. So if I look back at this chart, 386 falls somewhere between 361 and 400. So we know that the square root of 400 is 20. We know the square root of 361 is 19. And the square root of 400, we said, was 20. So the square root of 386 falls somewhere between 19 and 20. Looks like it's pretty much about halfway in between the two of them. So since it's a little bit closer to the 400, we would go ahead and round it to 20. So we would say that the side length is approximately, and when I say approximately, I usually use squiggly equal signs. So it's not exactly equal, but it's almost equal. So this isn't an equal sign, but it almost looks like an equal sign. So it's approximately 20 microns. And you can see how that would be useful, if you don't have a calculator to get to the nearest tenth or the nearest hundredth. It's really hard to take the square root of 386. But this makes it a lot easier knowing that the square root of 361 is 19 and the square root of 400 is 20. Therefore, you know 386 is somewhere in between there. Okay, we classify numbers using sets. And a set is nothing more than a well-defined collection of objects. And these objects are called elements of the set. A subset is a set that consists of the elements from the given set, and you can list the set with these braces, these little squiggly things, and you'll get good at writing them. I always get asked, how do I write them? You'll know by the end of the year. We do this over and over again. And in my classroom, you'll notice on the back wall that I have listed for you the subsets of the real numbers, and we're going to be using those quite a bit. And Mr. Bradford will use them again in Algebra 2 quite a bit. So go ahead and pause the video, and I would like for you to make this chart on your paper, and the numbers across the bottom, go ahead and put them into what category you think they belong in. Okay, so let's look at these. If you notice, the numbers that are down here in the natural numbers category end up falling in every single category above them. For example, 1 is a natural number, it's a whole number, it's an integer, and it is a rational number. And that makes sense because looking at the chart, the little circle is inside of all of those bigger circles. And we know that our natural numbers are the numbers that we naturally count by. When we're counting, we start with 1. 1, 2, 3, 4, 5, 6, 7. And when we move up to the category of the whole numbers, all of those natural numbers are in there. But notice, now there's a 0 in here. And 0 isn't in the natural number category. I always think of a donut hole. You know, 0 kind of looks like a donut, sort of. So the whole numbers are all of the natural counting numbers, and then you add the donut hole because they're whole numbers. So you add 0. I don't know. Might not help you, but it helps me. And then integers is now all of the whole numbers. Notice 0 is up here in the integer category. But it now includes negatives. So it's whole numbers and their opposites. Integers include the natural numbers, all the counting numbers, the 0, and all of the opposites. So 1, -1, 2, -2, 3, -3. And when I get up here to rational numbers now have fractions, repeated decimals, decimals that end. Anything that can be written as a fraction is a rational number. And then irrational numbers, we know, are numbers that never end, never repeat. So it's a decimal that never ends, never repeats. Like pi is 3.14, and it just keeps on going, keeps on going, keeps on going forever. There's no sort of pattern to it, and it never ends. Okay, so if you want to pause the video to write this down, you can do so. That's just basically what I just explained to you. The real numbers is all of those put together. The real numbers include all of those categories that we just talked about. So if you want to pause this so you can get this in your notes, that way you have examples to look back at, that would be good. So classifying real numbers. Go ahead and pause the video here as well and see if you can figure out what these are. So pause the video. Okay. And there are your answers. All of them are real. Every number we talk about in here is going to fall into the real category, so we don't have to list that every time. But the top 2 are rational. This -1.4583, it only falls into the rational category because it is a decimal that ends. So it's since that decimal's on there, it's not an integer, it's not a whole number, it's not a natural number. However, 15 is a natural number. It's a number we can count by. It's a whole number, it's an integer, it's rational, and of course it's real. And the square root of 57, it's not a perfect square, so it is irrational. Okay, an inequality is a mathematical sentence that compares the values of 2 expressions using an inequality symbol. We have the less than, the greater than, less than or equal to, and greater than or equal to. I want to read those in the order which I had them written. So when I'm comparing real numbers, I've got to figure out which one's bigger, which one's smaller, and then put the appropriate symbol in between. And you've probably heard in the past the alligator mouth opens up towards the bigger number, wants to take the bigger bite. So we'll use that same analogy in here. So what is an inequality that compares the numbers, the square root of 17 and 4 1/3? What do you think? Pause the video and go ahead and try and see what you can come up with. Okay, so if you take the square root of 17, you will get 4.12, and it keeps on going. So square root of 17 is equal to 4.12, I think it was 1, 2, 3, I have to look at my calculator. Yeah, 1, 2, 3, 1, 0, keeps on going. And I knew that it was going to be really close to 4 because the square root of 16 is 4. So the square root of 17 has to be just a little tiny bit over 4 because the square root of 25 is 5. There's a big jump from 17 to 25. So I knew it had to be really close to 4. And then, of course, 4 1/3 is 4.3 repeating. So which of these is larger? Obviously, the 4 1/3 is the bigger one. So when I put in the alligator mouth, I want to eat the bigger number. So the square root of 17 is less than 4 1/3. And what is the order of the square root of 4? 0.4, negative 2/3, square root of 2, and negative 1.5 from least to greatest. Well, to be able to compare these, we have to have them all written in a similar format. So we need to either have them all expressed as fractions, all expressed as decimals. So let's just go with simplifying all of them and putting them as decimals. So we know the square root of 4 is 2. And of course, this is already a decimal. I know that this negative 2/3 is the same as negative 0.6 repeating. Square root of 2. It's going to be less than 2, obviously, because the square root of 4 is 2. The square root of 2 is 1.414. And it keeps on going. And then we've got negative 1.5. And it wanted me to list them from least to greatest. So the least would be the one furthest left on the number line, which would be negative 1.5. Next would be my negative 0.6, which was originally negative 2/3. So then next we're going to have the 0.4, just moving right up the number line. Then the 1.414 was the same as the square root of 2. And then last of all, we had the square root of 4. So there are our numbers listed in order from least to greatest. For some reason, my video is giving me a really hard time recording this year and posting, so I'm sorry. I'm not sure what of that cut off or what it left. But we changed them all into decimals and then listed them in order from least to greatest. Okay, so if you would like just a little something extra to try, you can try this one on your own. And this is actually that same problem, but what I did was I copied it over here so that you could paste it along the number line so you could kind of see the order listed from least to greatest.